Perfect.
Uh, okay. Okay, I will just provide you an overview on the tidal and wave energy potential and its application along the Indian coast. But prior to that, I'll also just discuss about the global scenario. And my connection, I think it should be okay. In case of any problems, please let me know. The organization of my lecture today are given here. I'll just start with an introduction, then operational wave and tidal plants around the globe. I'll touch upon the tidal and wave power potential, and then developments in India in brief. Then wave energy conversion, that is it is now abbreviated as WEC. And then I on the wave energy conversion, which looks more promising than the other forms of ocean energy. I will just devote slight additional time. I'll start with the principles, site selection, strategy, classification of wave energy converters, then pilot plant in India, different concepts of multi-purpose, because standalone wave energy converter is not that giving a good cost benefit aspect. So, and then I'll try to summarize at the end. If you look at the ocean energy, the state of art. So, for example, what are all the kinds of alternate sources of energy you can get from the ocean? So you can get the tidal energy from the variation of tide, then marine currents. Then these currents may be induced by tides, or there can be permanent currents inside in the ocean, or offshore wind, which is very promising these days. And there are a lot of developments in the offshore wind. Then ocean thermal energy conversion. Even our country has tried something along the Kulasekara and then ocean waves. This is getting a lot of prominence. And then salinity gradient, not that explode yet. So this is from the basic introduction. You see that we have at least half a dozen forms of energy from the ocean that can be trapped. So that can be tapped. So it is it experiences, it provides us different natural opportunities. Technologies unequally developed, unevenly developed. Then investments has not gone in a very big way in some of the types. Then experience from prototype shows that most of the prototypes are pilot plants. It shows that wave energy technology is more promising. So an overview of the wave and tidal potentials. So you have from the tides, the currents. The currents can generate current by simple, you see something like a windmill under ocean currents. So if this moves, then that can be converted into electricity. So now if you look at this, capture energy in underwater tidal streams, upsides, that is the benefits. It is having extremely dense energy source, highly predictable. You can easily predict. Then promising economics, at least as of now on papers, because there are so many losses of energies when you talk about the potential and what you get in final. Then it is of course scalable. Then there are downsides that are daily slack intervals. Then underwater devices difficult and costly to service, less widespread under than the waves. Prospects, I would say, although I have written it as good, it is good only for a few selected places. But then moving on to estuarine tides, we have it's almost like a dam engineering. So we have enough experience on the installation of hydroelectric projects, hydropower projects. So it is something like you build up the water on one side, and then that head can be used for driving a turbine. So it has some downsides, it has some environmental impacts. The capital cost is slightly high, and there are again limited number of sites that can permit this. Then coming to the waves, which seems to be more promising, and in fact, India has IIT Madras has been playing a very important role on the generation of electricity from the ocean waves. In fact, we had a pilot plant installed in early 90s. Now, This can be actually floating or shore based, etc. I will go into more details on this. But one thing you should notice that it is the prospects are good in medium and long term, uncertain for a short term. Now, if you look at the major operational tidal and wave energy plants worldwide, so you have major operational tidal plants are based on tidal barrage. So you have a barrage and then you use that head of the water for converting or running a turbine. Or maybe you have a flow of water due to tidal difference where there is a tidal variation of, see, for example, Gulf of Cambay, you have a tidal variation of about 10 meters, or Bay of Fundy, that's somewhere in Canada, you have the largest tidal range in the world, which is to the extent of 17 meters, because within 24 hours, you can have 17 meters of water depth going from zero. So that is what is the tidal range, which can generate currents, and that can be used for driving the turbine. The earlier slide showed a small animation of the current, the what do you call that? Something like a windmill rotating. So the same thing, the logic would hold good here. So you have so you see the countries, South Korea, France, Canada, China, and Russia. They have they have installed all this tidal barrage, and the capacity of the installed capacity is given here. And similarly, the tidal stream, this is tidal power, that is that barrage based tidal power, and then this is a tidal stream that is based on the tidal current. So you have all these plants. Oh, sorry. So you see that it is all the way from UK. So UK has played a very big role in this area. US, then France also is there. So then we move on to the major wave energy plants that are in operation in the worldwide. So you have, of course, China, Scotland, Japan, Norway, and Norway was also one of the earlier thing. One of the thing which is missing is the Bergen plant, which was very promising, but I think now they have stopped. Then you also see we are happy to have Vizhinjam here, and hats off to IIT Madras, which gave us the first pilot plant early 90s, because actually the planning was started, the studies were taken up by late 80s, and then we came up with a pilot plant in 1996, which I will briefly touch upon. And then Portugal also has been working on this area. Now you have the Central Electric Authority has identified this. I'm talking about developments in India. So as I said earlier, the work on IIT Madras was started early 80s, and then we had the first OWC plant. OWC, I'll explain about the principles later. I'm just giving you the overview as of now. The first wave energy plant was installed in Vizhinjam, that is Kerala, that can generate electricity. It was almost like a pilot plant installed in a water depth of 10 meters. So then, so you see the view of this plant which was installed. Now it has been decommissioned, and then we also had the NAOT, which is called as you have a buoy which is moving, and then this will trap the energy from the waves, and then it can generate from through. It will run a turbine, and the electricity can be. This was only just a starting stage, but still a long way to go. But in IIT Madras, we are still working on the number of concepts on the OWC. We have been very strongly working with Italy and Norway. We had sponsored projects. It's very difficult for me to cover all the aspects. We have at least produced at least 3 or 4 PhDs on this particular topic. And some of the information, if you want, you can just go to my website at IIT Madras, and then look at my publications, and you can download some of these publications, which are quite handy. Then Atlantis, this is a tidal stream which is still in the docking stage. Then we'll move on. Now, status of existing tidal and wave energy projects in India. So Kalpasagar, that is in Kambat, Gulf of Kambat, the capacity was this much, yet to start. And then the cost is also given. I don't want to touch on each and every aspect. Gulf of Kambat, again 50. So this was the one which was also, this is only in a conceptual stage. Then this was planned, but unfortunately dropped. So there are some problems with the tidal power. Then we are again looking at the Kalpasagar project, and which is taking shape, and some of my colleagues are involved in this. I'm not involved in this tidal because I don't work tidal energy. Then I have already mentioned about this. The work so far done is not so appealing, but it has served as a stepping stone towards a brighter future. So let's wait and watch. Now, prior to that, it's very important to have an assessment of the tidal power potential in India as well as tidal wave energy potential in India. So when you look at what exactly is a tide, the tide is nothing but the rise and fall of the water surface in the ocean, which is just a static head of water. It goes up and down all over the ocean. So the tidal range, that is from the lowest level to the highest level, this is called as the tidal range, and in between them is called as the MSL, which all of you have heard. So the tidal range of Tamil Nadu, say, is of the order of only around 0.75 to 1 meter. And if you go along the coast in this direction, it keeps on increasing. And if you reach around Bengal, it's of the order of 4 meters. And if you reach Gujarat on the west coast, it is of the order of around 10 to 11 meters. So this rise and fall can always be helpful in driving a turbine. So next, so an overview of our approach in the estimation of tidal power. So we know the concept, but before that, we have to estimate the potential. And next, we have to, after estimating the potential, we have to look at the concept, and then we have to come out with the conceptual design, and then we try to go in for a pilot plant, and then we make it commercial. This is the route in which we need to travel. For that matter, it is the case with any kind of projects. So what we have done is the tidal power, uh, the tidal level at various locations along the Indian coast is found using the National Hydrographic Charts and WX tide, and performing an harmonic analysis. The site conditions like tidal range, current speed, water depth are the governing factor for energy harnessing technology. So now tidal levels prediction has been validated by deploying some of the sea level gauges that can easily measure the tidal range at several locations and along the Indian coast. Now, this is the Indian map where you have you see the tidal range. So we have the neap tide and spring tide. I don't want to go into the details, but we look at the spring tide variation. The spring tide variation, as you can see, are of the order of about 4 meters, but it goes up to about 11 meters somewhere in Gulf of Cambay. So naturally, the Gulf of Cambay is important for is a more promising area for installation of tidal power plant. It has all other environmental impacts, which needs a careful understanding and detailed investigation prior to installation of the other kind of other locations are given here. So I don't want to read all those things, and we see that it is more or less not several locations are not many locations are available for the tidal power extraction. Now, based on this exercise, we came to know that the tidal power plant, tidal potential along the Indian coastline, there are only 3 regions in India with a large concentration of energies. These are Gulf of Kambat, Gulf of Kutch, Sundarbans regions, because of the large tidal range. That is why I said west coast and east coast. So as you go down up the tidal range increases. However, the table also brings out the fact that it is not only the tidal range, but when it is going up and coming down, it can generate a lot of currents. And these flow velocities are enhanced at the openings of coastlines. It has some natural features that accelerate the current magnitude. It is possible in that case to realize reasonably good amount of kinetic energy. Hence, for the region with a low tide range, the obvious choice will be to modify the flow pattern of the tidal flow, ebbing and flooding, that is going up and going down, so that reasonable currents can be. So two things. One is when going up and coming down, that is the tidal range. So you use something like a hydropower plant. The other one is because of this, the current generated. So you use the kinetic energy of this. So based on this, we have identified some of the locations here. The tidal range is given here. The average available kinetic energy per square meter is also given in watts. So this gives us some kind of an idea, and because this is the basic thing which we need to go further, to proceed further. Now we move on to assessment of wave energy potential. How big can be a wave? So this brief, a small movie shows you how big can be a wave. Because we normally go to the beach, we look at the waves, and then we see the waves breaking. And once the waves are breaking, you have a gentle uprush of the water, and that's what we normally see. But the waves can be as high as you can see here. So much of energy is available in the waves. So the but then now what you need is the waves are an oscillatory motion. What do you mean by oscillatory motion? The surface of the wave can easily be defined by a simple harmonic motion. That is, a sinusoidal wave can be sinusoidal motion can be used to represent the oscillation of the free surface. So you see that if the bottle is there, it will be remaining in that portion, in that location, and undergoing a circular or an elliptical motion. I will not go into the details. For students who are looking at my lecture, and if they want to know more about the wave mechanics, I suggest you just type my name along with ocean waves in the YouTube. I'm sure that you are going to get lectures, or you can visit my website. Now, for the benefit of students, I have uploaded all my YouTube lectures in my own website, so you can have a ready access. So now the waves are defined by the height, by it. So this may be the mean sea level, over which you have the oscillation, and the distance between the topmost point to the bottommost point is called as a wave height, and the wave height will be increasing, and then when you come very close to the beach, then it breaks. This is what we normally see. And the waves are characterized by the height, its height, and the length. What is the length? The distance between successive topmost points, which is called as a crest. This point is called as a crest, and this point, bottommost point, is called as a trough. The distance between this is called as a wave length. So the wave power in a wave is a combination of h square, is a product of h square into t, or h square into L. I don't. So now the wave. So this picture shows the wave power potential that has to be estimated. How it is to be estimated? It will be varying with respect to the wave height and wave period, and this is what is called as the power. So this has to be estimated all along the coast, or at the locations where you propose to think of installing. So you have to have good wave height and period. So these are the two parameters that control the wave power. So now if you look at the distribution of energy around the world, these are the uh, values in kilowatts per meter of the wave front. Wave front is when the wave is moving in this direction, wave is moving from this direction. Towards my right is the coast, and towards my left is the offshore. So this is how, this is what is called as the wave crest. So, or the wave front. So you see that we don't have much of the wave potential. The wave energy potential is only 14 kilowatts per meter, not much. And uh, and also one more important information is, so we do have monsoon, maybe in September or October. So during that time alone, you will have a very high energy. Then rest of the times you will have not even 20% of that peak energy. So there's no point in thinking of such kind of a site as a potential site. You need to have the distribution more or less uniform so that you can get the energy throughout the year. So that is one of the important aspect of wave energy. Now, present approach. So we did some calculation of wave energy potential. So but in fact, the first paper for a wave energy potential was brought out by myself. It's a single authored paper that was published in 1982 in the journal Ocean Engineering. So wherein I have estimated the wave power potential, and I have given the complete details. And there itself, I have mentioned that standalone wave energy for India may not be feasible, or may not be yielding fruitful results. But if you combine it with something else, then probably you might look at the cost benefit aspect more positively. So now the data sources are the wind wave model. We have used what is a wind wave model. I will not go into all those details. We have used what is called as the WAM, which is a third generation wind wave model, which can utilize the wind characteristics to generate the wave characteristics, the offshore. So based on this, we have developed, we have used, and some of these data, wherever there are some measurements available, we could validate. First is validation of our numerical model. We have validated, and after validation, we have estimated the wave power potential along the Indian coast. So this is more recent compared to what I have estimated long back. So we earlier estimate was something like this, and now based on a more refined way of doing it, because what we have I had done in early 80s was the offshore data based on which visually observed observations from flying ships in the offshore. But this is more reliable data from the wind characteristics. We generate the wave characteristics and we get this. So you see that these are some of the areas where you have a good amount of energy. So waves, the power potential is given here. The different colors shows for different magnitude, considering the coastal regions where power is about greater than 10 kilometers, 10 kilowatts. So then this gives us a blueprint of where exactly we can think of installing or planning for a wave energy converter. But that is step number one. But step number two, remember, it has to be linked with some other thing. Only then we stand to gain. Otherwise, I don't think it may be really meaningful. So the summary of the wave energy potential are given here. So you have the different states, maritime states, along which you see the power potential variation, as you can see here. So then now, having evaluated the wave energy potential, now look at the selection, site selection strategy. How do you site? As I said earlier, availability of wave power. So that is the first step. Then whether there is any local demand. Number two. Actually, one more thing is whether, as I've already told you, whether you can link it with something else. Something like you get a byproduct from the wave energy plant. So that is one more criteria, very important criteria, which you need to have it in mind. So now device selection strategy, whether one of the thing is you can integrate the coastal protection system with the wave energy converter. This is an idea which is coined from by us, and we are going in a very strong way in this. And I am proud to say that IIT Madras has recently tested, and many of the papers we have published in the AACE, Journal of Waterways, Oceans, and Coastal Division, and recently also I think one of the paper right now it is there in the production. So if you are really interested, just look at some of our publications, so that can show you some more interesting facts. So wind dominated. So the other area is wherever you have offshore wind, you can try to combine offshore wind with wave energy units. It's always good to combine, but of course, initial investigation has to be from one mode and then try to combine two modes. Now, coming to the energy conversion. So input is from the wave energy. So from wave energy or the wave power, you are primary energy conversion to conversion to energy in pressurized area or water, or in you compress it. Then the secondary conversion is by turbine or hydraulic motor, mechanical energy by rotating a shaft. So then finally, all these things will lead to electrical energy. Now, most important is the energy losses. So energy from ocean waves, you have a primary when you are doing the primary conversion, you have losses. Because even by calculation also, because the wave elevation is going to vary at random, so even that is going to change even what is available energy in the waves. Whatever we are talking is the average energy, but this is going to even have a slight deviation from the average energy. Then energy in working fluid, what is the kind of a driving liquid that is going to take care? Is it air, water, or hydraulic? So these are all the things which are going to act as a driving fluid, which is going to drive the motor or the turbine, which we'll be seeing later. Then once the turbine is rotating, then you have also, when the turbine is rotating, naturally you will have the mechanical energy in the rotating shaft, which can lead to some amount of loss. Then finally, like so, you see how challenging is extraction of energy from the ocean. So efforts are towards the reduction of loss, thereby to increase the efficiency of the device, and that is where IIT Madras has been playing a dominant role in our country. So wave energy devices. So based on the principles of three principles, basically three principles. One is focusing the wave energy. The other one is pressure difference due to oscillation of the surface of elevation. I mean, the wave is going to bounce like this. So according to the difference in pressure, you can have one principle, that is another principle. And the relative buoyancy, that is, you can have a floating device which oscillate in the wave, and that can pump in energy. So these are the three basic principle based on which the wave energy converters work. And then I will some of the examples of how you can understand some of these principles. For example, prior to that, we will just look at the based on size. One is based on the principle, that is the focusing of wave energy, the pressing difference, and the buoyancy. Now, based on the size, see, you can have the terminators. Terminators mean the waves energy is being transmitted. So you have a structure here, and structure can be some width, and the entire energy is going to go into the waves, and then the energy is going to be trapped. That is what is called as terminator. The wave which is coming towards the shore are completely stopped by a terminator. The other one is the attenuator. In this is the lies in the principle of wave direction. So wave direction is there. So you have a structure which can move. So now the that is the wave is so having in mind. The waves are coming. This is your coast, and this is the waves are coming. So again, here this is the coast, and this is the coast. Now here the structure will be normal to the shoreline, whereas here it will be parallel to the shoreline in the case of terminator. In the case of attenuator, it will be normal to the shoreline. That is a major difference in its orientation. Now, in the case of the point absorbers, these are floating structures. These are floating structures with components that move relative to each other. So you can have a number of floating structures which will be moving as per the wave action, and a floating buoy inside a fixed cylinder, something like that. So it's so once the waves are moving, so this also will be moving in this direction. So you can have a number of them spread over an area, and so they will all work in unison to produce the required power. So now if you look at this animation, it will be very clear. Now we are talking here about the terminator. So we have a natural terminator. You look at the left hand side. So it is a natural terminator. So you see the waves going inside that rock. So there are two, this one. So waves are coming out. So the energy is coming out. That is, what is this basically? What is this? This is releasing air. Releasing air, that is, in between when the wave are trapped here, there is an air column which is releasing that air. That air column is going to drive a turbine, and that is what is explained here. And this concept is called as oscillating water column device, which the wave energy plant of India is also based on, and we have also been doing on working on this concept, trying to improve it further and further. So now you see that I'll just explain this. So here you can have a look at this. So what will happen is the energy will go. There is a small hole here, and this is called as air vent. This air vent is very important. So this the size of the air vent, we have done a lot of research and then found out how much should be the air vent for the maximum air to be sucked out, so that it can drive the turbine. So now the size of the hole is very important. That is going to depend on the characteristics of the waves. So when the wave is moving within this enclosed chamber, so this alone is open, so it moves in, and then this air column oscillates. So this is called as, in fact, this oscillating water column creates an air column, and that air column drives a turbine, as you can see in this animation. So this is the working principle of the terminator, which is so now you see this is the point absorbers, wherein you have some kind of a system which is moving up and down, and that is going to compress the air, and that compressed air is going to run the turbine. So you can couple a number of such items, such floating bodies, and that can be used for supply, production of energy. So this is point server, and now this is the attenuator. I hope this works. Anyway, I'll come back to that towards the end of the lecture. I think it's not, the link is not proper. I'll just come back to that later. Now, classification according to location. Now, we have seen how these are classified. Shore-based, near shore bottom standing, floating, near shore, offshore, bottom standing or submerged, not too deep water, submerged, not far from water surface, hybrid units of above types, combined with conversion energy. But what is this? See, shore-based is very nice. The one which you saw, a natural system, So in fact, in Norway, which is called as the Bergen energy plant, that is also mounted on a cliff. So that serves as a natural area for using it as a wave energy converter. Now, near shore bottom standing, That is the one which is going to be, which was installed in India. I'll be discussing. Floating and other things are not at, it's all still under investigation. All the other things are all under investigation. So more popular are the first two ones of first two. Now classification, so much of information is available and so much of work needs to be done. So it is for the youngsters to take it up as a challenge and work in this quite a promising area. So in the case of according to energy conversion, you can have a overtopping device. Overtopping device means you have something like imagine that there is a tray. You allow some waves here come and fall into the tray. That level static head of water is going to increase. So that static head of water can drive a turbine. So that is the principle on of overtopping devices. Then you have the wave activated top. Wave activated means you can structure up and down, maybe a buoy or something like that, which we have already seen, that can be utilized for the generation of electricity. And finally, the oscillating water column, which I already explained. So these are all the different kinds of overtopping device. I just something like a buoy, which so the buoy up and down. So you see there is a pump here. This is moving up and down. This pump and pump required energy, and that energy can be into your electrical energy. Then you have the oscillating water column, which I already said, and you have this is what is called as Saltus nodding duct. This is one of the earlier version of the wave energy converter, wherein you have a spine, you have a kind of a duct called as not. This was installed. This was invented by one professor from University of Edinburgh, and he, in fact, he was there with us early, I mean, late 80s when we organized a workshop, and he was there with us to explaining this principle of nodding duck. Only thing is you have to be careful with all the moorings, etc. And this is also quite promising, but it was not. It just stopped with lab work. Now, fundamental things. I will skip this. I will move on to the oscillating water column. So the principle, the oscillating water column is a device used for extract. What is the thing? Energy of the waves is converted into high pneumatic energy of air, and then this is converted into mechanical shaft. That is, so the generator generates, the turbine generates unidirectional pulsating torque. Only one important thing which you need to know is the air column is going to move up and down in this direction. So when it is moving in this direction, see, it is not like moving in one direction. If it is moving in one direction, you know, there are several turbines like Pelton wheel or so many turbines which we have seen. So it will be, there is no problem in generating the power. But here the movement is in two directions. So irrespective of the direction, the turbine has to rotate in one direction. So that was the challenge. And one Professor Wells from UK, he invented what is called as a Wells turbine. And later there are a lot of other developments, including IIT Madras. One of my colleague is working on this turbines. A lot of work, effort have been put in, and still it is in research stage. So coming back to oscillating water column, where which will be the focusing point of my lecture, the turbine is on the above the water table, water, and it is the only moving part. So when you have anything moving underwater, it always poses a challenge, particularly in maintenance and also avoiding or reducing the losses incurred. So it can be easily integrated with the coastal works. That gives us an idea. Then operation is land-based, and maintenance is also quite easy. Disadvantages: radial flow have more impedance and the opening depth controls performance. So all this, so what are the important things? Based on the wave climate, we have to design what should be this depth, what should be the width, what should be this horizontal, all these things. So the size itself is very important. Not only the kind of surface here, should it be horizontal, or it should be like this, or it should be a curved. All these things we investigated through Indo-Norway project, which I will share it with you. Prior to that, you look at the OWC in Vizhinjam in Kerala. So this was a demonstration plant, design, installation, and valuation, and semi-commercial prototype, etc. So then now this is another view giving you some of the details. So the dimensions are given here: 24 or 23 meters by 17 meters by 15 meters. Then impulse turbine coupled with induction motor. Then axis. This was installed long back, and it proved that it can generate electricity. And after that, there were a lot of maintenance problems, and finally it has to be given up. This was installed of Trivandrum, and in a water depth of 10 meters, wherein there was a bridge also established from the breakwater, existing Vizhinjam breakwater, to the OWC. So this was, as I said, this was the first stepping stone. Then when I was invited to Norway for on some assignment, so there I was looking at different concepts, how to link the OWC as integrate, how to integrate. So there are some concepts which came into my mind. So this is what I have shown here. For example, you have a simple thing, small craft, fishing harbors or so. You can have something like this, very simple. It can be moved maybe up to about 10 meters water depth. You can have some design like this, and this opening, etc. We have now done a lot of studies. So all these things can be proved to be useful, at least in the future. So I'm sure that someone may take it up. And then, or you can have on this one, you have a harbor wall. This is harbor wall. See, what will happen is, how do I show the harbor wall? So, okay, now this is the OWC. So these are what is called as harbor walls. The Norwegians proved that construction of harbor walls on side of the OWC, as you can see here in plan. This is a section. You have the OWC. Now OWC, the wave will come, and then this is oscillating water column, and then this is for berthing of structures. So you can integrate a berthing structure here along with the OWC. Either it can be moved or it can be fixed, but then this OWC will permit the wave and oscillation will take place. The energy can be converted, and then this harbor walls was proved to be more effective in increasing the in enhancing the energy or the efficiency. And that is why I have retained these harbor walls here in this concept. So the same thing here with, and so you can also have without, there is no sloping structure. So now I have put a sloping wall. Maybe the energy is directed and amplified here. So this also we have taken up as a PhD work, and we have done a lot of work, and then I will show you some of the typical results soon. The other concept is something like this. You just have no harbor walls, just have sloping wall, as you can see here, and then a caisson, and this is used for berthing. So this is for deep berthing structures, so coupled with OWC. Or you can have something like a structure, as you can see here, a framed structure, and this is built up over this, and then you have the vessels berthed here. So here in this concept, what is the idea is, this entire structure can be moving up and down. Only the heave motion is allowed. So then in that case, the relative motion is going to be a challenge. But again, these are all concepts which need to be further investigated. as one would say, the fixed structure is supposed to give better performance, but anyway, it needs to be investigated further. So the same thing here. So I've just given some of the concepts which we came up, and then we looked at through the Indo-Norway project. What we did is we took what should be this depth, what should be this opening, what should be the air size hole, and what should be the type of floor. So we considered 1:5, 1:1, one that's the horizontal, and also a curved uh, floor. And then we looked at what is the run up, that is how much is the run up, how much is the wave run up. The wave is going to run over this thing. That is important in order to assess how much of power is going to be inside this chamber when the wave is oscillating. Then we wanted also from the structural point of view, what is the not only structure, from also from the hydrodynamic point of view, what is the pressure that is being developed here on the here, etc. So we looked at some of the aspect as well as the hydrodynamic aspect. And this person, John Ashton, now currently is in the University of Prague, again continuing the similar kind of work on ocean energy. So these are the model investigations, the model setup in the waveform, where we have housed a number. So this is 1:1, 1:1.5, 1:5, sorry, and then this is the curved bottom, and then this is the flat. So the energy, this is the beach. So you see the wave energy going from here. So a number of wave gauges were installed, the pressures were measured, all those things were done. And then the salient results only I'm just presenting here. So this proved that a circular arc, that is this one, proved to be very good. The efficiency is the comparison in the case of wave amplification factor. How much is the energy being amplified within the oscillating air column, and also its efficiency are shown here. So even if you look at this kind of variation, the kind of variation also really matters, because finally we are going to deal with several losses of energy through several quarters, So it is very important to address all these things. So one of the important thing is this A by A, that is the air vent size to the area of plan area of the entire thing is so that is this area versus this area, that is air vent, relative air vent. So we found out that it is approximately 0.68 or 0.65 is the best possible thing. And this is one of the important conclusions we have drawn from a series of studies. And then there are other studies also. Is there any problem?
Network problem, sir. You can, yeah, now it's okay.
Okay. Okay. So now studying the studies on linking of wave energy converter to detached breakwater. So this is where we are playing a very important role right now, and this again is part of Indo-Norway project. But then we have taken it now. We are doing a series of studies. The same guy has completed part of his studies. So what does this mean? So you have horizontal breakwater. These are breakwaters are nothing but trapezoidal cross sections constructed with rock material. So this is so when you put these structures like this, these are called as offshore detached breakwaters, and in between these gaps, they are constructed in order to combat coastal erosion. If there is a severe coastal erosion, if you place this properly, which is usually determined by numerical model studies, which we have been doing a lot on this aspect. So if you can house this properly, then you can protect, particularly in case of islands, you can protect this by offshore detached breakwater. And if each of these breakwater can be housed with a and oscillating water column. So this I have already told you. So now I will move on to what is that we have done in the lab. What we have done is, you see that this is a breakwater, conventional breakwater. We have taken a number of chambers here, and each of these chamber we have put a we have installed a oscillating water column with a curved slope based on whatever we have determined, and then we have subjected it to, so the spacing between the OWCs was also varied. For example, and then we found out which is the kind of spacing which would give us a good amount of efficiency. So you see that these are the detached breakwaters. So this is one breakwater, portion of the breakwater, and this is the portion of the other breakwater, and this is the central breakwater, which is housed with 5 pieces of the OWCs in order to understand its performance. So what we did is thrice the width of the center to center model spacing, absorb the power to a maximum of 2.2 times the incident wave power. This is an important conclusion drawn by us, and this is the first time we have such kind of a study carried out in our entire globe, in fact. So now I'm coming to the final slide, wherein the schematic view. This is our concept, which is still there lying in our head, and probably I don't know when it come to reality. Uh, when we want to have harbors formed by breakwaters, and you can have a number of oscillating water columns, and then the oscillating water column will absorb the energy and send it as electricity for the house, and at the same time lead a calm area for berthing of vessels and passenger vessels, or whatever it is. It can be for anything. So typical site selection now. This is our idea. Now only 5 sites showing potential implementation. In fact, a number of COSUS sites can be chosen along the entire COSUS stretches where, say, power is greater than 10 kilowatts per 10 kilowatt. So the choice of these are highly arbitrary, but it is only to show that the potential sites along the various maritime states under different site conditions. So what we have chosen is Maharashtra, Kudal, then Trivandrum, that's in Kerala, Kanyakumari in Tamil Nadu, Puducherry, Pondicherry, and Andhra Pradesh, somewhere in Kaviti, based on some of the power potential. This is only on power potential, but then the ideas can vary or differ, because tomorrow, see, someone can come and tell that Lakshadweep Islands, there are a lot of erosion taking place, and electricity is a big problem. So that could be a possible site where you can protect the island with detached breakwaters housed with oscillating water column. So these are all in our mind, and let's see how it goes. So as engineers, we need to work on optimized designs for wave energy collector, installation, power conversion systems, moorings, power system, power transmission system, then generation control, and maintenance, and decommissioning. So you see each item has a lot of input and lot of effort, lot of action involved. So we are doing is only a small aspect of the entire studies which are being discussed. So I'll come to the summary. So let me start with the energy potential. They can be installed only in large scale, not in small scale. Then potential locations have been identified, and I have shared with you. New technologies are emerging, new areas also emerge. There could be possibilities that for 10 megawatt size plants in low potential areas, we don't know, because someone can come out with some innovative ideas. Tidal energy has become more practical over wave, but because the prediction of tide is much more easier than wave. But then for some reasons, the wave energy seems to be more promising, and that is the reason why you have a number of wave energy pilot plants coming up all over the globe. In fact, if you look at the way all these things have developed, it was okay. So if you look at the whole developments, what is happening is the wave energy in the early 2000s. Say, for example, 1900s. So 19, I would say, uh, 1990s, 1990 to 2000, there was a very highly talked about wave energy and ocean energy in general and wave energy in particular. But then there was a lull period. People were not talking about ocean energy at all till 2010. So one decade there was not much of work. You can just check the literature. But again, after 2010, it has taken a rapid increase in the wave energy. So this is based on my personal observation. And that is why when we wrote proposals on wave energy, immediately it got accepted. We got a major project from European Union and also one from Norwegian Science Council. So wave energy potential, many potential sites have been identified. I have shared with you most common cost-effective solutions would be integrating with existing port structures or newly developed port structures. Research is underway at IITM for concept evaluation of hybrid wave energy converters so that civil costs could be cut down. These are all some of the things. And now I would also like to say, I'm happy to say that we have just published a book on ocean wave energy systems. So it is Professor Abdul Samad and Professor Sanasraj, myself, and one of our postdoctoral fellow, and we have edited, and this was published recently. And if you want to know about other things, if you want to understand about ocean wave hydrodynamics, I have published recently a book by World Scientific, and I think 2 months back this book has come out. And similarly, this has come out in another, I think 6 months back. So if you are interested, you can go and check all these things for details. And also you can visit some of my webpage for some lectures if you are interested. So acknowledges to Crisis Limited because they only gave us the study to be carried out, and that is what I have shared with you. The general information only I have shared with you.